Ladies and gentlemen, welcome to video 19 in a series of video lectures that are companions to the book The Fivefold Sun, filed at the Bibliothèque Nationale de France in Paris in late 2017. We are today November 26 in the year 2018, about a year later, and we address now the issue of the geometries that are possible, that are conceivable, and the probabilities associated with these in the partitions of the solar ball as suggested in this book. In video 19 we start with introducing and briefly investigating these possible geometries for the numbers of partitioning balls in a circumscribing sphere of either 14 and 13 for the long cycles and either 11 or 10 for the shortest cycles. We first turn to the possible geometries in the partition of a solar ball. In the case of the longest cycles, 13 and 14 balls, and in the case of the shortest cycles, 11 and 10 balls. We will now have a look into the geometry of a circumscribing sphere's partition into certain numbers of balls, starting with the number of 12 balls in the case of a regular icosahedral partition. These are 12 balls that are arranged in hemispheric sets of 6 balls, and as you remember from video 9, in which we built such a set of 12 balls with magnets, we arrive very easily at a perfect arrangement. And the magnets, when they are magnetized in the same direction, will also aggregate in this way very neatly. Now we will consider the case with, instead of 12 balls, either 14 balls, i.e. 2 more, or 10 balls, i.e. 2 less. And we avoid in the first step, the odd numbers of balls. We avoid the odd balls. We now consider the case with 14 balls. In this box you can see 2 rings of 6 balls. They are staggered as in the case of the 2 5-ball rings in a regular icosahedral arrangement as shown before. These are now magnets as in video 9, and the magnets, which were all magnetized in the same direction, allow and in fact necessitate such a staggering of the 2 rings, which have a total of 12 balls. They are tangential among themselves 2 by 2 in the top hemispheric ring and same in the other hemispheric ring, and they interpenetrate at the equatorial plane. Now if we add a 13th ball on top, it will not be fixed in position as a polar ball. There is a room for this ball to move, and if we added a 14th ball in the bottom as a polar ball, it would be also not fixed in position along an axial polar direction. So we have here the case for 14 balls, which is somehow analogous to the case for 12 balls. We now consider the opposite case for 2 balls less than 12, which is 10 balls. And we start with this set of 8 balls, which again are magnetized in the same direction. And maybe some of those who look at this video will be surprised to see that the magnets impose that the 2 hemispheric squares are not staggered, as opposed to the case with 5-ball rings for the icosahedron and the case with 6-ball rings for the case with 14 balls. They cannot be staggered. The magnets impose that the two squares remain always in this position. Now if we add the ninth and ball on the top as a pole, it hardly fits in position. The magnets do not allow a pole on top to align, and if we added the 10th ball at the bottom, we would have a more distorted shape. So that is the case for 10 balls, and you see that it is extremely far from any irregularity. It is, so to say, much worse than the case with 14 balls. We now turn to the intermediate cases, which are actually apparently can be inferred from observations of the length of cycles in the Sun, the cases with 13 balls and 11 balls. In the case with 11 balls, we have a choice of starting with an arrangement with 10 balls and adding 1 ball, or starting with the arrangement with 12 balls and subtracting 1 ball. This was already suggested in the video in which we discussed the transformations of the solar ball during solar maximum epoch at polar reversal, in which was suggested that one could subtract from 12 slots one of the balls, leaving 11 balls in 12 slots. In the literature about the Coulomb-Thomson problem for point charges on a sphere, several authors suggest that this would be the least distorted configuration, just withdrawing 1 ball from the 12-ball configuration. In this case is lost mirror symmetry about the equatorial plane if a toroidal ball is subtracted, or is lost the polar alignment if it is one of the polar balls that is subtracted. The second possibility is to start from the case with 10 balls, which is highly distorted, and to add 1 ball, but it will be difficult to reach as much regularity as in the previous suggested scenario. So with 11 balls, in any case, we are in a highly distorted situation. In the case now with 13 balls, we can also start from the 12-ball configuration and add 1 ball, or we can start from the 14-ball configuration and withdraw 1 ball. We start with this scenario now, starting from the 2 rings of 6 balls that were postulated for a 14-ball arrangement, as indicated by the behavior of the magnets that we here use in this experiment. The top pole that was suggested in this arrangement brings the total to 13. If we forego southern bottom pole, we have the 13-ball arrangement. We keep a mirror symmetry about the equatorial plane, but have lost 1 pole. What is more, again, this pole is not fixed in position, but this is a minor distortion as compared to the situation with 11 balls. We can also start from the 12-ball icosahedral arrangement and add 1 ball. The result was described in the video about polar reversal at solar maximum in the solar sphere, in which was reported that the 13 spheres fit in a subscribing sphere and have a central angle of only 58 degrees approximately, as opposed to the 63-degree icosahedral angle in the case of 12 balls. So in this case, starting from the icosahedron with 12 balls, we lose both the polar axis alignment and the equatorial plane mirror symmetry, because of the quasi-regular common central angle of 57 degrees between all of these 13 spheres. All in all, we arrive in both cases for these intermediate geometries with 11 balls and 13 balls to a confirmation of the assertion in the previous video that regularity is broken, and thus there will be a non-zero dipolar field in such arrangements. But we have loss of stability and loss of symmetry that will be detrimental to any regularity in the numerical kinematic of a solar cycle in these circumstances. We now turn back to the case for 13 balls, in which we forego the preconditions of having equatorial mirror symmetry or axial alignment, and we set the condition that the outer balls must be tangential to the circumscribing sphere, as in the case of an icosahedral setup. With 13 balls, we saw in a previous video that the arrangement which satisfies this condition was described by Schutte and van der Waarden. In this 3D model, we try to reproduce this Schutte and van der Waarden configuration, the characteristic of which is central angle, spheres of slightly less than 58 degrees. As you can see, the glass ball circumscribing sphere is a little bit offset because we will not find any polar alignment of sets of two mutually antipodal balls. As you can see in the bottom, there is here a ball which is centered so as to be a southern polar ball, but on the top there is a slight tilt of the center of the top ball compared to an antipodal position, which would be an axial alignment, for example, for a rotation axis. Also, because we have 13 balls, it is impossible to have two hemispheric rings of 5 balls each, supposing that we have a set of almost antipodal balls, which we subtract from the total of 13. In the toroidal area, we have 11 balls instead of 10 in the icosahedral setup. So now we have in the bottom southern part of the arrangement 5 balls, and in the top part 6 balls, which are quasi-parallel to a quasi-equatorial plane, but we cannot define a strictly planar equatorial area, and we cannot ensure that we have exactly 5 and exactly 6 balls in the respective hemispheres. In fact, the entire arrangement is irregular. You see this ball is at a lower latitude compared to this ball, and it is the same for all of these balls. So this is the circumscribing sphere arrangement, the Schutte and van der Waarden arrangement, which is perhaps realistic in the case of the Sun, if it must be partitioned into 13 balls in trying to be as isotropic as possible. So it is suggested here, or say conjectured, that such Schutte and van der Waarden arrangement is what is underpinning the configuration of the fields during a solar cycle lasting 12.4 years, i.e. 169 rigid rotations, i.e. the square of 13 in numbers of rigid rotation. Please note that in this video, in this discussion today, this arrangement is suggested for a dipolar, poloidal cycle in the Sun. But what is interesting is that in the case of this 13-ball arrangement, as opposed to the 11-ball arrangement for a short cycle of 121 rigid rotations, this is also the length of a toroidal sunspot cycle of 12.4 years, of which we have 5 in the sunspot record. That is 1/5 of all toroidal cycles. In the case of the recent cycle number 24, which unfolded from 1996 to 2008, we can contemplate the possibility of a 13-ball partition because this cycle lasted 169 rigid rotations, the root of 169 being 13. There have been a number of remarkable anomalies in this cycle compared to the few preceding cycles, which were cycles of length of about the standard central value of 10.6 years. One of these anomalies were the very weak polar fields. Can we explain the weakness of the polar fields with the geometry of a ball partitioned in 13 instead of 12 outer balls? It is interesting at this point in the discussion to reflect on the notion of the presence of a poloidal cycle and a toroidal cycle to be determined by statistical behavior or by a more deterministic rationale. We start from an optimum that we suggested to be an arrangement, a partition of the solar ball in a 12-ball icosahedral configuration, which is a regular one. We see in the solar activity record in the sunspot time series that there is a departure from the standard length of the solar cycle, which seems to reveal a departure from a partition in exactly 12 balls. Of course, this can be regarded as a statistical circumstance. If we have a distribution of more or less irregular lengths in a phenomenon, the distribution has to be expected to represent a variety of slightly different lengths, and we have to expect departures. So a cycle of 121 rotations only, or as many as 169 rotations, compared to 144 with 12 balls, i.e. cycles with 11 or 13 balls, would have sooner or later to return to the mean of the length of the solar cycle, and we would be in presence of the behavior of a, so to say, statistical sun. But another rationale is conceivable. This rationale would be that the 11-ball and 13-ball partitions do not occur by chance, but because they are necessary for the production of a dipolar field. So instead of a statistical sun, we will have a more deterministic sun with two sets of preconditions for its cycle, one for the toroidal cycle, icosahedral, and one for the dipolar poloidal cycle. In this case, all the two sets of cycles constantly mutually superposed. Is the dipolar field with 11 balls or 13 balls constantly superposed? We can now try along this line to answer the questions from the end of video 17. This set of this sequence of three cycles for the open field. Again, this is a wrap-up. A first cycle with 121 rotations with, i.e., an inferred number as a root number of 11 balls. We suggest that in this case we have the icosahedral setup with one ball missing. This will be also the case for the second such cycle having the same length. But we can, as an illustration, propose that there will be so almost enantiomeric situation with one ball missing in one case and the antipodal ball missing in the second case. Here, for illustration, we propose to have the north polar ball missing in the first cycle and the south polar ball missing as an antipodal ball in the second cycle. This is suggested so as to mimic or to parallel the polar reversal situation in the toroidal field. And then a third cycle with 169 rotation, inferring a root number of 13 balls partitioning the solar ball. That is the 12.4-year-long cycle, which is a mode of the AA index cycle length. It is its second mode. And the 9.0 year is the other mode of the AA index. In total, we have 411 rotations, which is again about 30.3 years. You see now here the set of the suggested three configurations corresponding to the three characteristic lengths of solar cyclical activity, now in the case of the poloidal cycle. So here in the back is a configuration which is icosahedral, except that the north ball is missing. It is suggested to be the first of the three poloidal cycles which occur in a sequence. The second such poloidal cycle, again with 11 balls, is the same as the previous one, but what is missing is the south polar ball. And then the third cycle has a different length. Instead of 121 rigid rotations, it is 169 rotations. Supposing a root value of 13 balls, we have here the Schutte and van der Waerden configuration for 13 balls. You see that from in a front view, like we see now, you have a difference which is mainly four balls that you can see in the front view instead of three in the northern toroidal ring, revealing that there is one ball more than 12, and two almost quasi antipodal polar balls, whereas in the two shorter cycles with two balls less, there is one polar antipodal ball missing. So this would be the set of three cycles, of which consists the Sun's poloidal cycle: 1, 2, 3, 1, 2, 3, 1, 2, 3. Each sequence having 411 rigid rotations for 30.3 years, with an average length of 10.1 year. If we now try to answer the questions from video 17, we have to go through the issue of the relation of the poloidal three-cycle sequence, which is postulated here, with the toroidal cycle itself. Here we are left only with conjectures and with new questions. First of all, it is proposed that the poloidal 3-cycle is permanently superposed over the toroidal sunspot cycle, which occurs itself with 12 postulated balls and creates a closed field amplification over 144 rotations with a length of 10.6 years. Then we conjecture that the poloidal 3-cycle is partially synchronized, not only superposed, but synchronized with the toroidal cycle via the 10.1 year mean of the length of the 3 poloidal cycles. This is indeed also the second mode of the toroidal cycle. There is now the question whether this partial synchronization is a periodical synchronization. We will deal with this in part 5. We are now in part 4. Then about the 169 rotation cycle, the 13-ball Schutte-van der Waerden configuration is, as you just saw, less at odds with a icosahedral setup compared to the 11-ball configuration. Maybe it is close enough to the icosahedral setup to be able to force the toroidal cycle in some way to the same length. We have 5 sunspot cycles of 12.4 years, i.e. 1 in 5 in the sunspot record. This would be the reason why we have a mean sunspot cycle length which is larger than its median, because of the weight of these 5 long cycles. Another possibility is that the toroidal cycle deviates on its own from the optimal icosahedral configuration. Maybe in this case we will be back to the scenario of a statistical sun for the toroidal cycle length distribution. Finally, the 11 and 21 rotation cycle in the poloidal cycle with 11 balls departs very much from the icosahedral setup, and following the rationale about the 13-ball cycle, unlike the former, this short cycle would fail to force the toroidal cycle to the same length of only 90 years. This would be why this length is seen only once among sunspot cycles. We are left with the final question, why is this rotation cycle, 11-21 rotation cycle, indirectly present in the sunspot cycle length statistics via the mean of the 3 cycles lengths of 121, 121, and 161 rigid rotations, i.e. 10.1 years. How can this possible? Ladies and gentlemen, this question closes video 19. We will now turn to part 5 of the Fivefold Sun project in the next video. And we will focus on cyclicalities in the solar record, which are less than the solar cycle quasi-decadal length, or longer than this length. Thank you very much for your attention.